So after we had started looking at our stability and our rate in form of delta G and E activation, we had started looking at the 4 mechanistic arrow pushing steps that you all need to know for all ionic reactions. So we had looked at acid base, where there is a protonation and deprotonation of the proton. So remember, what is a proton? It's the H positive. Then we started looking at the nucleophilic attack. One of the forms of nucleophilic attack is when you have a strong nucleophile, a negatively charged nucleophile, attacking different electrophilic sites. We had also looked at a neutral nucleophile, a neutral protic nucleophile, for that matter of fact, and how that is attacking different forms of electrophile. And then we had started looking at the leaving group. Your leaving group, whatever is your leaving group, needs to be a weaker base and should be able to exist independently. So stable and weak, that's what it requires. Loss of leaving group can occur on its own or when a nucleophile, incoming nucleophile, kicks out an existing leaving group. So these are the two ways we have loss of leaving group. What if you do not have a good leaving group? Then what will happen? Then you have these two choices, these two different pathways, and we will look at these two again during our SN1 and SN2 mechanisms. You can either convert or replace this hydrogen with a mesylate or a tosylate or a triflate kind of a group, then introduce your nucleophile attack. So this is one kind of a reaction. This is a different part. You have already created a leaving group, the nucleophile attacks, the leaving group leaves, and you get your new compound. So from here to here, in these two steps, we have created this new material. Or you can protonate your OH. And why is OH a bad leaving group? Because remember, if OH existed on its own, OH or hydroxide is a very strong base. And what is the definition of a leaving group? A leaving group needs to be a weak base. Weak bases are great leaving groups. So when the proton gets protonated on this OH, water molecule will be released. So this will be your leaving group. But when this water molecule will leave on its own, so this is on its own leaving group leaving, this carbon will be left electron poor. And this carbon is defined as, electron deficient carbon is defined as a carbocation. So carbocation. So this is all about the leaving groups. And today we are also going to look at carbocations in more detail. But before that, let me quickly show you the solvents also. Okay, so this is just a repetition of your leaving groups. Oops. The solvents, and we already discussed protic materials. So in the same order, protic solvents are those solvents where a hydrogen bonding hydrogen will be present. Protic solvents will always have a hydrogen next to an electronegative element. For example, here it is next to an oxygen, here it is next to a nitrogen, and so on and so forth. So those are your protic solvents. Aprotic solvents, on the other hand, as the name indicates, will be without a proton. And for this course, you should know all of these polar but aprotic solvents. So if you look at this particular molecule, there is a C and there is a N. There is definitely a dipole present here. So the polarity is there, but no proton will be available to be given away. Similarly, in acetone, 1, 2, 3, a carbonyl. What functional group is this? This is a ketone. And this is a nitrile. This ketone is definitely polar, but are the hydrogens on this molecule protic? Can you give away these hydrogens? No, because if you try to take out these hydrogens, you will be making a C negative. And C negative is usually a very strong base. Right? So you can argue that, oh, there might be resonance, but before that, look at the atom. Atom will be very strong, and so it is not going to give you any protons at all. Similarly, dimethyl sulfoxide, or in short DMSO, or DMF also. So if you look at these few solvents, we will be using them exclusively for SN2. And I will be talking about SN2 by the end of today's lecture. What is SN2? Why do we need it there? And so on and so forth. So know your solvents. Know what is the structure of these solvents and how these structures are affecting your mechanism. So know your protic solvents, know your aprotic solvents. Any questions? Any questions? No questions? Okay. So with this formation, we are now at our, so A and B, these were just examples. The last mechanistic step is rearrangement. Now, what is this rearrangement? Before we can look at this, let us first look at our slides. Okay, let me show this. So before you understand rearrangement, let's try to understand what is a carbocation. A carbocation, as we had looked, has a positive charge on carbon and it has 6 valence electrons. Usually how many valence electrons are there? 8. But the carbocation has 6 valence electrons, and hence we say carbocations are electron deficient or electron poor. If something is electron poor, it is definitely an electrophile or an acid. But carbocations are Lewis acids, and that's the definition of Lewis acids. Lewis acids are materials who are electron poor or electron deficient. So all electrophiles fulfill that definition. They are very reactive and very unstable. So let's list out the properties of carbocations. First, it is sp2 hybridized. Who can tell me what is the geometry associated with sp2 hybridization? It is very good. Trigonal planar. It's a flat molecule. And these are electron deficient, 6 valence electrons, and hence an electrophile. Now, The next important thing that you will see multiple times is the stability of a carbocation. Now, before we do that, let me remind you what is the classification that we are using. So if you remember, if you have a structure like this, how many primary carbons are there? What is a primary carbon? A carbon which is attached to only one more carbon. Yes. So this is a primary carbon. Do we have any other primary carbons? No. What is a secondary carbon? Or how will you classify this carbon? This carbon is attached to two other carbons, and hence we classify this carbon as secondary. This carbon is secondary, this carbon is secondary, this carbon is secondary, this carbon is secondary. What about this carbon? This carbon is also attached to only two other carbons, and so this is a secondary carbocation. This carbon, how will you classify this carbon?
Secondary.
This is also a secondary carbocation because there are 4 bonds, no doubt, but 2 of them are with carbon, 1 with hydrogen, 1 with chlorine. So this is also a secondary carbon. This carbon right here
Tertiary.
is attached. Yes, very good, Sammy. This carbon is attached to 3 other carbons and hence labeled or classified as a tertiary carbon. So this is the exact same classification that we are going to use for carbocations. Okay. So besides the fact that your carbocations are sp2 planar molecules and the fact that they are electron deficient or electrophilic, the important thing that you need to know about carbocations is their stability, their need to become more stable. So why is that this particular order is so important for us? Allylic and benzylic are the most stable forms of carbocations. So this is a carbon CH2 with a plus sign here. This is your benzylic carbocation, whereas this is your allylic carbocation, A, B, C. So this carbon is labeled as C. On the other hand, vinylic and phenylic. So remember your nomenclature, module 2. If a hydrogen is missing from the aromatic carbon, that will make it a phenyl site. The phenyl site and the vinylic site. So one hydrogen is missing from this double bond area. That is your vinylic site. These are the most unstable carbocations, and carbocations would rather not form. More stability for the carbocation, the greater the chance for it to form. And that is what leads for us to remember any mechanism where a carbocation forms, you will see, if there is a possibility, the rearrangements. And knowing these rearrangements is very, very important. Okay. And why is that the carbocation feels more stable and all those sort of things? We're going to quickly look at that part also. So if you think about it, and I'm going to look at my tertiary carbon, I will compare it with my primary carbon. Okay. So if I'm a primary carbocation, at least one carbon is attached to me and 2 hydrogens will be attached, right? To this carbon, this is electron deficient, an alkyl group is attached. I don't know how long it is. It may be just one carbon. What is the ability of an alkyl group? The ability of an alkyl group is a plus I effect. What it means or translates to is that this methyl group will pump their own electrons in this carbon. Yeah. So for a primary carbon, this carbon feels stabilized because this other carbon is sharing its own electrons with this electron deficient part. On the other hand, if I have a carbocation which is tertiary in nature, what does this equate to? Because it has plus I effect, all of these three groups will be pumping their electrons into this electron poor carbon, making this carbon feel more stabilized compared to just one-sided plus I effect. This carbocation is feeling the effect or stabilization from all the three areas. And now let's compare it to a benzylic site. We say, oh, look at this carbon. This is so stable. This is the most stable carbocation. You cannot say that this is primary. Okay, even though there's only one carbon attached to it, we say this is a benzylic carbocation. So make sure that you're able to recognize also these structures in your molecules. Why is the benzylic the most stable? Yes, there is this alkyl group, so probably only one-sided plus I effect, but not just that. When we talk about stability, we always talk about the spread of electrons. That is what equates stability. The more spread of electrons that any molecule feels, the more stable it will feel. When we have a conjugate base, we always look for more spread of electrons. Electronegative atoms are spreading more. Bigger atoms are spreading even more. And resonance induction and induction spread, all of those are all because of the spread of electrons. So if we look at this particular structure, benzylic groups will be highly resonance stabilized. At least 4 resonance structures will be possible because of benzylic. How many will be possible because of allylic? At least 2. So remember, this resonance is very important for your organic chemistry. You must understand how resonance stabilizes a molecule. So among a benzylic, a tertiary, and a primary, who would be the most stable form of a carbocation? A benzylic carbocation. Now, resonance and rearrangement, they are two different things. When we talk about resonance, resonance is within the molecule and only movement of electrons. Movement of electrons. No atoms are moving. Okay, when we are doing resonance, that's what resonance is. But when we are looking at rearrangement, and we are going to look at the 2 rearrangements that I'm going to show you, we will see atoms moving. Yes, there will be movement of electrons also within the same molecule. So the primary difference that we see is in resonance, no atoms are moving, but in rearrangements, atoms will be moving. Any questions so far? Okay. So just want to remind you quickly, the allylic and benzylic are most stable. Tertiary is more stable than secondary, which is more stable than a primary. And this is just a methyl group on its own. Okay, so this is just the methyl group on its own. So between a primary and a methyl, the methyl will be less stable. And then the vinyl and the phenyl. So remember, the R group, the alkyl groups, will have a plus I effect, pushing the electrons to the positively charged stable part. And this feast, this part is known as the hyperconjugation. Okay, so this ability to feel stabilized, hyperconjugation, whereas this is resonance. Different words of electron spread. Okay, so this is hyperconjugation, spread of electrons. This is the resonance, spread of electrons. So when we are looking at rearrangements, let's look at this structure. I have a, let's say, bromine here. Okay, so by its own or on its own, the leaving group leaves, loss of leaving group. That is, let's say, the first part of my mechanism. What would be I left with? This carbon has this methyl group. So this carbon has a methyl group. This carbon had a bromine. Are these the only 3 bonds this carbon has? No, there's a hydrogen also that this carbon has. So I'm going to keep my hydrogen here. But my bromine is gone now. So minus bromide. Is this carbon still neutral? Hyatt, are you here? Armani, are you here?
Did you say my name?
Yes, Hyatt, I did.
Mm-hmm.
I was wondering if you can tell us if this carbon is neutral or will it have some charge?
I would say it's neutral.
So it has lost its bromide, and now
I'm
instead of
sorry.
having all the 4 bonds,
It's gonna have.
Go ahead, go ahead.
It's gonna have a positive charge.
Very good. And why positive?
Because it, first of all, it's lost the bromide, which carries the negative charge.
Exactly.
And yeah, and
So in this
dipole.
polar bond, thank you, Hat. Very good. In this polar bond, the carbon is the partially positive carb atom, and bromide, being the electronegative atom, will be the partially negative atom. So when this bond breaks, when the leaving group leaves, the bromide takes both electrons from this bond. So in one bond, how many electrons are there? 2. So this bromide takes both the electrons and gets that extra as a negative charge, leaving a carbocation behind. And so what are the properties of carbocation? It is sp2, trigonal planar. It is electron deficient, and it seeks stability in form of rearrangement. Every carbocation seeks more stability. For your course, it will only look on its adjacent carbons. So it looks nearby and sees that if I jump here, if the carbocation becomes a carbocation here, I will be a primary carbocation. But if I jump right here, I will become what kind of a carbocation? A 1, 2, 3, a tertiary carbocation. Any questions on what I just said? Okay. And so when you're looking at this carbon, which is a secondary carbocation by nature, if it jumps to this carbon, it will become a primary carbocation. If it jumps to this carbon, it will become a tertiary carbocation. And this is where our first rearrangement types come into play. The hydride shift. The hydride shift occurs. So I'm going to draw all the hydrogens between this carbon and this carbon. So this carbon already has a methyl group. There is a positive charge on this carbon. And I'm looking at this carbon. This carbon has how many bonds?
3.
Yes. But that's the ones that you can see. But does all carbons have only 3 bonds?
There is one more.
That is our hidden hydrogen. Don't forget about it. I'm going to make this hydrogen a red hydrogen. So this carbon has a positive charge and this carbon has a hydrogen. When I say hydrogen shift, a hydride, a H negative, electron rich species will be moving. Remember, all our electron charges, all our arrows are moving from electron rich to electron poor in a curved arrow, full complete arrows. So this is what we are going to see here. The hydride shifts on this bond. And what do we get? We will make our main structure just like that. This hydrogen stays here. This methyl group stays here. But what has shifted? This hydrogen has shifted to this carbon. What has happened? This carbon got all its 4 bonds. But now this carbon, the other carbon right here, has lost its bond.
Positive.
So this carbon has lost its bond. Now it is electron deficient, and this is how it gets its positive charge. This is just hydride shift. Any questions on hydride shift? Everybody understands it? Okay, very good. Now the second part of rearrangement is when you have a alkyl shift. What if on the carbon that you want to jump on, you do not have a hydrogen? What you have is simple methyl groups or some alkyl groups. So let's do this. Loss of leaving group. So leaving group leaves. The bromide leaves. And we generate a carbocation. Portia, are you here? Portia Thompson. Okay. Taylor Medlin, are you here?
Yes.
Okay, great. Taylor, can you help us figure out what kind of a carbocation is this? How would you classify this? Primary, secondary, tertiary, alkyl, aryl, benzylic, what kind?
Secondary.
Very good. Now, more than secondary carbocation, do you think it can arrange itself or go itself to a better location to become a more stable carbocation? Do you think that is a possibility here?
No.
Okay, thank you, Taylor. Thank you very much. And that's a very good help that we have figured out that this is a secondary carbocation. In case you get a carbocation like this, you know, I always tell you to remember that carbocations will rearrange. Even if it cannot rearrange, you should still seek the possibility of doing that. Okay. So this carbon looks at this carbon and says, oh, if I jump here, I will become a primary carbocation. But if I jump right here, I might become a more stable carbocation. And this is exactly what the carbocation will do. On this carbon, I have one hydrogen. Remember, there were 4 bonds on this carbon. 1, 2, 3, 4. One of the bonds leave. I still have these 3 hydrogens. But now, on the carbon that I want to jump on, I don't have any hydrogens. What do I have? I have methyl groups or some alkyl groups. And now an alkyl shift will occur. So a methyl, so it doesn't matter which one of these, is going to shift here. And I will see a alkyl shift. Since the alkyl which is shifting is a methyl, you can label this as a methyl shift also. So I'm going to make all of my main chain. This is the hydrogen right here. I'm going to make one of my methyl groups also right here. But now this carbon will get what? This carbon will get methyl on it. What will happen to this carbon? This carbon had 1, 2, 3, 4 bonds, but now one of the bonds has shifted. It is now electron deficient. So from a secondary carbon, you will get this tertiary carbocation. So remember, this shift, this rearrangement will only occur between adjacent carbons. So 1,2 hydride shift or 1,2 methyl shift or alkyl shift. Remember, for your course, if a molecule has something like this, okay, then you cannot have this jump. Why? Because this carbon is next to this carbon and this carbon only. You don't have to look further than 1,2 kind of a situation. So here it is 1,2, here it is 1,2. So don't jump farther off. I mean, for advanced courses, we do that, but for your course, stick to the adjacent carbons only. Any questions so far? So no rearrangement will occur here when the carbocation will form. Any questions? Let's do one more. So this is A example, and this is my B example.
I have a question, please.
Go ahead, Sammy.
When BR is leaving, why you don't take 1, 2 shift hydrogen shift from the next carbon?
What?
No, this one in the bottom.
The bottom?
Here,
no, there will
yes.
be no rearrangement. So that's what I was trying to say. When the leaving group will leave, a carbocation will be generated at this carbon, right? A carbocation will be generated here. So it will only look at the adjacent carbon. It can only look at this carbon or at this carbon. It is already a secondary carbocation here, right? If it jumps here, it will still be a secondary carbocation only.
Okay,
there will be no change in the stability.
It should be tertiary carbon.
If there was a possibility, if there was a tertiary, if there was a possibility of becoming a tertiary carbocation, then it would definitely jump.
Thank you.
Okay, very good. So now here you had same methyl groups. Same alkyl groups. What if you have propyl? So do you remember what is a propyl group? Propyl is 3 carbons long, and this is a methyl with just 1 carbon. And I have this leaving group. So now when the leaving group leaves, and I see that I have a secondary carbocation, the secondary carbocation does not want to become primary carbocation, but it wants to become a tertiary carbocation. If you have a choice, you will always move the less bulky group. Do you understand that? So to move a smaller group is easy as compared to a bigger group. So when you're doing alkyl shifts, or even when you have a hydrogen and a methyl group or a hydrogen and an alkyl group, always try to move the smaller group first. So between a hydrogen and a propyl, you will always move the hydrogen first. Similarly in here, you will move the smaller methyl group. And remember, I'm not drawing it here, but the hydrogen is still there. So this alkyl shift occurs. The carbon gets the hydrogen and the methyl. The propyl stays where it was, and this new carbocation is formed. Any questions so far? Go ahead and draw this structure. For this particular structure, would you say, if I have to attack a nucleophile, would you say that I will get only one kind of a product or 2 kind of a product? Okay, so in all of these cases, you know your carbocation is here. If a nucleophile attacks, the nucleophile will go to these locations only, right? So you have this particular intermediate carbocation. How many types of products will be possible from this carbocation? Only one or more than one? So remember, whenever you look at carbocation, always think about what? Rearrangement. Is there a possibility of having a more stable carbocation? Armani, are you here? Armani?
Yes.
Okay, great, Armani. Armani, can you help us in figuring out what kind of a carbocation is this? How would you classify this carbocation? That's fine. Don't worry about being wrong or, also.
I'm not sure.
Okay, so if you look at this system, how many carbons is this attached to? And remember, there is a third hydrogen bond, of course. So how many carbons is this
2.
attached to? Very good. So ideally, it should have been a secondary carbocation. However, if you pay attention, there is a double bond, right? So now tell me, do you think it'll be just a secondary carbocation or a different kind of a molecule? It's a different kind of a molecule. And can you guess what it is?
Allylic.
Allylic. Very good. So before we finalize on a secondary carbocation, always look around. Very good, Armani, and thank you so much. So this right here is a secondary allylic kind of a carbocation. Why secondary allylic? Because this carbon is attached to two carbons, and that's why it is labeled secondary. And it's not just secondary, it is a secondary allylic carbocation. Do you see how I have classified this carbocation? So now this carbocation is quite stable already. Why? Because benzylic and allylic are considered as stable. Is there a possibility that this carbocation can become even more stable? Anybody? Take a guess.
No.
I'm sorry?
I said no.
No? Okay, Nelson, thank you very much. How about if I do a resonance? Okay, remember module 3 is not going to leave us. Nope. I'm going to keep everything exactly the same and let me do this resonance.
Benzylic and allylic carbocation.
Exactly,
Gotcha.
exactly. This is a secondary allylic, still secondary allylic, but also benzylic. Do you all see the difference? So this part is resonance. This is not a shift. This is a shift where your atoms are moving. This is just plain resonance. By resonance, you created another resonating structure. And this resonating structure is even more stable. So besides doing these hydride shifts, methyl shifts, even if by doing resonance, your structure, your carbocation can rearrange to more stable carbocation, it will do that. Okay. So I think this example should be under resonance and not alkyl shift. But just understand, don't just focus on one carbon, look around it also. Okay, so knowing if a structure is going to rearrange or not, that is a very important part of your reaction and mechanism knowing. So pay attention that when you were doing the leaving group breaking, you were doing what is known as a heterolytic cleavage. Heterolytic. Lytic literally means cleaving or cleaving off. Hetero means uneven. So when you have this bond of C and Br, you know that Br is pulling the electrons towards itself and becoming something like this. When the Br leaves, it does take all the electrons with it. So there is this electron and then there is this electron. The Br takes both the electrons, leaving the carbon as a carbocation. Okay, so this is a heterolytic cleavage or heterolytic bond breaking, which will generate your carbocation. So these are the 4 methods: acid-base, nucleophilic attack, loss of leaving group, and rearrangements. These are the 4 mechanistic arrows that we will be using again and again and again to develop our mechanisms. Okay? And the first mechanism that all of us are going to look at are the nucleophilic substitution reactions. What does this mean? Nucleophile is a electron-rich material. You will have a substrate where there will be an electron-deficient atom, or you will have a leaving group on your atom, which will be making this carbon still electrophilic. So this is complete formal charge, and this is a partial positive charge. So this is your substrate. In a substitution, either of these will give you a nucleophile attached to this system. Either the leaving group will leave, or if it is only electrophilic, it will just attach itself. So substitution just means you substitute one group for the other. Please make sure that you read from the book the details of all the nucleophilic substitution reactions. Okay. I also have a handout on our drill in the content section. So besides the sequence sheets that I have for you, where you will see the differences between SN1 and SN2, how to figure out what is SN1 and SN2, I would also like you to look at this handout. Where is that? Oh. So probably during this weekend, I would like you to look at this handout where I've just concised all the information about what is a nucleophile, what is a base, who are the stronger nucleophiles, and then what are the protic and aprotic solvents, and so on and so forth. So, but make sure that you read your book first, and so you can get a deeper idea of how we are trying to look out for these substitution reactions to determine which substitution reaction will be we are looking at. And so whenever there is an already existing group of an atom or a group of atoms and an incoming nucleophile comes and attacks, that's when you get a nucleophilic substitution. And we have already looked at the different kinds of leaving groups. For example, the halogen atoms and the OMS and the OTS and the OTF. And so if you have a nucleophilic part, for example, I have SH, CH3SH. This is my nucleophile. The lone pairs of the S can attack. And I have a group with a fluorine, same nucleophile. I have a group with chlorine. Which of these will be reacting faster? The point here is you have same nucleophile, similar substrate. What kind of a substrate is this? This is a secondary carbon, and so this is a secondary halide. This is a secondary carbon and this is a secondary halide. But the point is that your F is a bad leaving group. And this is something that you have to remember. Great leaving group. So while this will take a long time, this will attack, nucleophilic attacks, leaving group leaves, and you get a new material. Because it was neutral, you will get a positive charge here. Deprotonation will occur. And this bond breaks to give you your new product. Who in this class does not understand what I just did? So this part, nucleophilic attack, we have already looked at when we did our neutral protic material reacting. Instead of having NH2, I just have SH. This is still protic material attached to an electronegative element. So when the neutral material is attacking, the leaving group is leaving. I did the exact same thing. I know this is my electrophilic carbon. Why? Because the chlorine is polar. The next part is removal of this protic hydrogen, which is the deprotonation part that I did here to make my molecule neutral. Is there anyone who does not understand this? Okay. Now, we have already learned about the bases in our module 3. So in this module, we will be focusing more on nucleophiles. And as I said, nucleophiles are also electron rich, just like bases. Just like bases, the size of the atom helps make the nucleophile even more stronger. The only difference between a nucleophile and a base is it does not like no bulk on attacking atom. And this can be evident from a hydroxide example. If I have a OH and to the same oxygen, I have a tertiary butyl group. Remember, this is a tertiary butyl group on oxygen. OH and this O tertiary butoxide. Between these two, this oxygen and this oxygen are exactly the same. But if we consider this, this will be a better nucleophile and this will be considered as a better base. Why? Because nucleophiles do not want any bulk on them. Okay, and I think on one of these slides, right here, we see the difference even more. And I think we discussed the nucleophiles and the bases yesterday also. Just to remind you what are nucleophiles and how they are different from our bases is also an important part of your this chapter. So make sure that you read it better. Nucleophiles need to move and attack fast. So we always look at stronger nucleophiles. There are some of the groups which can act both as a strong nucleophile and as a strong base. But there are only few of these. We will look at other conditions also when we are looking at that. Yeah. So when we are looking at any nucleophilic reactions, and we'll look at some more, we assume that there is solvent. All of the reactions are working or occurring in a solvent. It might be acidic solvent, it might be a basic solvent, the protic solvent or the aprotic solvents. Okay? Unless a solvent can actually determine or differentiate or make a different product, we usually do not write it on the arrow. So unless we feel that it is going to change the mechanism of the reaction. Another thing that we do not write on our reaction arrows is temperature. We consider that all the reactions are being held at room temperature. Do you know what is room temperature? In degrees Celsius. Anywhere between 20 and 25 degrees Celsius is considered room temperature. Anything below it is considered cold. Anything above it is considered warm or hot. So even if you're given 30 degrees Celsius, you will consider it as a heat. Okay. So we will now be looking at our first reaction mechanism. And what is a mechanism? A reaction mechanism is just a way of depicting steps or consecutive steps that account for the overall transformation of reactants, where we use mechanistic arrows. Okay? So remember those 4 mechanistic arrows. We will be developing our mechanisms from all of those. When we will be looking at a reaction mechanism, we will look at 3 things. We will look at the rate, we will look at the stereochemistry, and we will also look at regiochemistry. Now, don't be afraid of all these names that I'm calling out. So rate, who will work faster? Just a few seconds ago, we had already started to look at it. Who will react faster? This will react faster. Why? When the conditions are almost exactly the same, the only thing that was different was the leaving group. And we know that because CF will be held up tightly and F is not considered a weak base, it is considered as a strong base. We still know that this is a bad leaving group. And so this is what we are going to introduce: the rate of reaction, the stereochemistry of the reaction, and the regiochemistry. And we are going to look at these terms in the coming classes. So before we start with our SN2 mechanism, I want to remind you that acid-base reactions, which we have started looking at in Module 3, are still the most common reactions that you will see. So if a protonation or a deprotonation can occur, it will occur over the rest of the reactions. SN2 are the next most common reactions. Okay, so SN2 are the most common substitution reactions. So after, based on ARIO, you have decided that an acid-base reaction cannot happen, but a substitution reaction will occur. SN2 should be your first choice. SN2 looks like there are 2 steps. So 1 step, 2 step. But it is really a concerted step. What does a concerted step mean? A concerted step just means it is occurring one after the other, naturally. You know, when an apple falls from the tree, the apple doesn't have to stop midway in the air and then stop midway in the air, again stop midway in the air before it reaches the ground so I don't break up or crash into half. The apple just falls naturally. So that is what 2 consecutive steps, a concerted step, means. And the rate determining step is evaluated by both your incoming nucleophile and the substrate that your nucleophile is attacking on. Any questions so far? What does concerted reaction step means? So now, since both our nucleophile and the substrate are important, we say that this is a second order reaction, a bimolecular order rate. Okay, so this is the rate, the order of the reaction is second order. What does this mean for us? If I will change the concentration of the other, I will have to look into the concentration of the first one also. So if I had a rate, and we did this example on our first part. if I have an example, generic example, both the concentrations of A and B are being affected, and if I double the concentration of A, my reaction rate becomes 4 times. What happens when I will double the concentration of B? Let's do that. If I double the concentration of B, what will be my new rate become? Rate double prime will be K A raised to power 2 to B 1. And so when I will compare these two rates, rate prime over rate, it will indicate that my reaction will become 2 times. My reaction rate will double if I will just double the other substrate. If I double one substrate, this is what is going on. But the order of the reaction is 3 times. So SN2, on the other hand, is a bimolecular nucleophilic reaction where both the concentration of the substrate and the nucleophile are important. Now, when you're looking at a SN2 reaction, if you understand the transition state and the 5-membered transition state that it has, you will be able to make your substitution determination life very easy. Okay, because everything, all the conditions that SN2 requires is dependent on this 5-membered carbon transition state. First of all, this is the only time you will see carbon have 5 bonds. For the rest of the time, remember, even if your carbon is carbocation or a carboanion, and we'll look at carboanions sometime in future, both carbocations and carboanions have 3 bonds. They cannot have more than 4 bonds. So this is a one-step concerted or simultaneous bond making and bond breaking reaction mechanism. It is bimolecular. When the two groups collide, the nucleophile and the substrate both collide. And there is a backside attack. What does that mean? Because of the probability that a 5-membered transition state has to form, there will be bulk, there will be crowding all over. So this part of your carbon is a flat part. Okay, OH on one side, that is the incoming nucleophile, and the Br on the other side. Br, or the leaving group, as we say. So let me draw this kind of a wedge and kind of a thing, wedge and dashes kind of a thing. I have, let's say, a hydrogen here, a methyl here, and let's say I have a hydrogen here also. And I'm going to attack what? NH2. NaNH2. So in my NaNH2, Na, because of it is a metal ion, will still have the positive charge. Nitrogen will have the negative charge. So this nitrogen, is it going to attack from the same direction as the leaving group? No, it does not want to do that. Why? Because unless it attacks from the back side, opposite side, the anti-side of this bromine, so I'm just going to draw my hydrogen, methyl, and this hydrogen. All of them are in that same flat plane. My NH2 will attack from one side. My bromine, or my leaving group, will leave from the other side in one single unidirectional flow. And so my NH2 will be entering at one end, whereas my bromine or my leaving group will be entering from or exiting from the other end. So when this happens, this leaving group leaves, this leaving group has left the building or the structure, I will get what? I will get a hydrogen, a methyl, a hydrogen, and this NH. If I do my configurations here, which I cannot because this carbon is not chiral to begin with, but let's say if this carbon was chiral, let me make it as OH. Okay, just to make our lives a little interesting. Now this is a chiral center. This is also chiral center. But this chiral center and this chiral center are flipped. So what we say is that an inversion of configuration. What does inversion of configuration means? If this was R, now this is S. If this was S, now this is R. Completely opposite. Inversion of configuration or stereochemistry has occurred. Any questions on what I just did? Because of this 5-membered transition state, I could point out that I will get an inverted configuration. Why? Because my NH2 and my leaving group, they both need to be in the same line. If both of them are on the same end, if I introduce my NH2 from the same side, when the bromine is leaving, it will kick out the NH2s, other molecules of NH2. So there will be a couple of NH2s here. If they try to approach this electrophilic carbon here, the bromine leaving will bump into these and probably not leave and will stay back. But if the NH2 attacks from the back side, it'll be easier. There'll be nothing here. So it'll be easier for the bromine to transition out. So looking back at this mechanism, what are the few things that you must ask yourself? Where is the start of your arrow? The arrow will always start at the electron-rich site. It will always end at the electron-poor site. Has the octet been destroyed? Yes, the octet is being destroyed here. Carbon cannot accommodate more than 4 bonds. But in the same time, the Br is acting as your leaving group. So eventually that octet will be maintained. The next question that you must ask is this leaving group easy to go? Will it go when the nucleophile attacks? If your answer is yes, then your product will form. So if you know your transition state, you will also be able to figure out several other things. Okay, so this 5-membered transition state, which we are talking about, cannot accommodate bulk also. So if these hydrogens were bulky groups, this 5-membered transition state would not form. And it has been determined by several studies that when a SN2 is reacting, the substrate is the biggest culprit for a SN2 reaction. So for SN2, because it cannot accommodate bulk, methyl groups are the best way of doing SN2, followed by primary substrates, followed by secondary substrates. So this substrate that we are talking about should either be a primary substrate or a secondary substrate, or just a methyl substrate would do. The best with methyl because least bulk will be present. And it can still work with the secondary carbon. So bulk is a big problem for SN2 reactions. Another thing that this transition state needs is aprotic polar solvents. Now what would happen if I did not have a aprotic solvent? What if I had a protic solvent? If I had a protic solvent, what would my protic solvent do? My protic solvent will give out protons, and these protons will aggregate around my nucleophile. What does my nucleophile need to do? My nucleophile needs to move fast. But with this clustering around it, with this aggregation around it, this will slow down. And that is the second thing that you need to know about SN2. It needs strong nucleophiles, which will move very fast. So strong nucleophile just does not always mean that they are electron donors in form of negative atoms. It also means that they need to be able to move fast. Any questions on what I just said? So having protic solvents in SN2 would not work well. Aprotic polar solvents is what will stabilize our transition state. So if you remember, what does a polar aprotic solvent look like? It looks something like this. These will have partial negative charges. Partial negative charges will be able to aggregate around this transition state, giving the leaving group and the nucleophile time to react. There are a couple of things that we have to remember about SN2 reactions. And the first thing is the substrates. For SN2, you need smaller substrates. For example, methyl, primary, secondary, no reaction with tertiary substrates will you get for SN2. What is the nucleophile that you need? You need a very strong nucleophile. Negatively charged, smaller in size. What is the stereochemistry for the product that you're going to get? You will get inversion of configuration. Okay. And this is what your energy diagram for a SN2 would look like. I think better than this, you can look at the sequence sheet that I have prepared. Where I've written all the requirements that you need to do. Whenever you will look at any nucleophilic reaction, make sure that you scan the substrate first. What is the substrate? Where the leaving group is, or a functional group that you have to change. Okay, that's what you need to figure out. So you can get your electrophilic atom, or the atom we are going to attack something. So that is your substrate. Then make sure that your substrate, what kind of classification you will give it to. Tertiary, secondary, or primary. Okay, alkyl halides, and then OTS, and then OMS. Those are great leaving groups. That's what you should have. Nucleophile, what kind of a nucleophile do you have? Do you have a negatively charged nucleophile, or you have the nucleophile which only will give you lone pairs, which are neutral nucleophiles? Then the leaving group that you have on your substrate should be a good leaving group. What are the examples of bad leaving groups? The one with H negative, OH negative, RN negative, C negative. And these need to be converted into good leaving groups. Okay. Solvents. Then if the solvent is given to you, then also you have to make sure that you have apolar or polar. Polar just means, oh, I should have written protic. This is protic versus aprotic solvents. Both of them are polar, definitely, because of the polarity involved in them. With SN2, you will only have the inversion of stereochemistry of the product. So knowing your SN2 is very important. You have to know which bond will be breaking and which new bond will be forming. And so if you know your transition state, you will be able to figure out the mechanism also. Let's do another example here before we move on to other group. Let's say I have this structure and I have NaSH. Now, a few minutes ago, I had used CH3SH. Now I'm going to use NaSH. Okay. What is the kind of substrate that I have here? This carbon is secondary. The chloride on it is also secondary. So this is a secondary substrate. This is my electrophile. I have a good leaving group also in form of chloride. What is my nucleophile here? This is my substrate. I have the leaving group, nucleophile. What is my nucleophile here? N, A, S, or H. Which atom will I start my attack from? Na is positive, S is negative. So this S negative is going to be my nucleophile. I have a secondary substrate. I have a strong nucleophile. These both, and I have a good leaving group. All of this is pointing towards SN2. Remember, the first choice of your substitution must be SN2. If the conditions of SN2 cannot be fulfilled for a substitution reaction, then we look at SN1. But whenever you're given an option for SN or substitutions, you must first give priority to SN2. So what is going to happen for our mechanism? The nucleophile will attack and the leaving group will leave. Now, the Cl is going at the back. Where is the hydrogen of this carbon? It is coming out. But when I will be drawing my product, my Cl will go back because my Cl has gone away. And this hydrogen will now go back. So what will be on my wedge now? The SH. What has happened here? To my stereochemistry of product, an inversion will happen. Why? Because I have decided this is going to follow the SN2 mechanism. Okay, remember SN2 is concerted. Everything happens simultaneously. So there is a backside attack. In one smooth attack, nucleophile kicks out the leaving group from the other side. But no bulk will be afforded on this 5-member transition complex. So the type of substrate has to be less substituted. So secondary can still bear it. The less hindered carbon will be attacked, the faster it will be attacked. So if I have these two same groups, Cl now H. So now for the same nucleophile, same leaving group, but is my substrate the same? No, my substrate is now a primary substrate. And so out of these two, both of them will follow SN2, which will be faster. This will be faster. Why? Because of less bulk. The transition state will form faster and my overall reaction will be faster. So the substrate, the bulk on the substrate is the biggest factor and the first limitation of SN2. Okay? So remember, your nucleophile also needs to be a strong electron donor. So go ahead and write out these in your notebook or page. And today we will also be doing a quiz towards the end of the class. So after we do these examples, we will just jump to our quiz. Okay. So go ahead and write out these, and I will ask some of you to show me your paper when we are ready for it. So remember what all you have to look out for. You have to look out for the type of substrate. You have to look out at the type of leaving group. Then you look at the nucleophile, and then you look at solvent, if solvent or temperature conditions are given to you. Based on that, you will decide your mechanism, your stereochemistry. Is your molecule going to be inverted, and so on and so forth. And you will also decide the rate of reaction. For example, let me do one of these for you. Let's do this one. On this particular substrate, this is my carbon of electrophilic nature. OMS is a great leaving group, and it is on a primary substrate. What is my nucleophile here? This sodium ion is positively charged, and the oxygen next to it is a negatively charged. Before that, can an acid-base reaction take place? No acid-base reaction can take place. Let's focus on substitutions only. This is a strong electron donor and hence a nucleophile. So I'm going to do my SN2 mechanism. The nucleophile attacks, the leaving group leaves. I will draw my main structure, but now instead of OMS, I'm going to add this oxygen, the carbonyl, and the CH3. So this is what my new product will look like. Right, and don't forget, this has the hydrogens, which I did not draw. Don't forget those. So if I have this molecule and I have this molecule, same nucleophile, who is going to react faster? Same nucleophile, same leaving group, but now I have a secondary substrate. So compared to a primary substrate, secondary substrate has more bulk on it. It will give me the product, there is no doubt about that, but this will be a little slower. Any questions on between this? Let me give you one more example. Let me use the same leaving group. But instead of this resonance stabilized electron donor, let me write CH3 CMgBr. So Mg is magnesium, will have positive charge. Carbon next to it will also have a negative charge on it. This is 2 plus minus 1 here, minus 1 here. Out of these two, both of them are primary substrates, both of them are same leaving groups, but now I have changed my nucleophile. Who is a stronger nucleophile? The carbon with a negative charge. Compare it to this molecule, which is just oxygen, plus resonance stabilization makes this a weak electron donor. There's stabilization, the spread of electrons on these three atoms. It is no doubt nucleophilic, but not as strong electron donor. So who is a more strong electron donor? This is. And nucleophile attacks the electrophilic carbon, leaving group leaves. By this carbon will have CH3. Oh, this will also have CH2. CH2, CH3. So this will be faster than, say, A, B, and C. Faster than A. Slower than. Okay. So why don't you finish these three on your own, and we will now go to our quiz. That would be the last thing that you do for the class today. We'll continue from here on Monday.